Hello everybody, my name is Živko Kokolansky. I'm an associated professor at the Faculty of Electrical Engineering and Information Technologies from Macedonia, and today I will give you a lecture. The lecture is entitled Signal Conditioning and Data Acquisition. What I would also like to highlight is that this lecture is supported by Erasmus Plus project, Action Key 203, with the project entitled Innovative Teaching Approaches in Development of Software-Defined Instrumentation and its Application in Real-Time Systems. So let's get started. This is the outline of my presentation, and as you can see, it is divided into 6 main parts. Actually, we will start with a very brief introduction to sensors and data acquisition, and we will discuss about some basic sensor model, some analog and digital signals and their properties. Then we will continue with the signal sources and their wiring to the data acquisition systems. Actually, we will highlight the grounded signal source and the floating signal sources. Next, we will discuss about coherent interference and suppression, or actually the effects of noise of the data acquisition systems. And we will then stick to the electrostatic interference and electromagnetic interference. Then we will continue with the grounding and the shielding of the cables which are used to connect with the data acquisition cards. We will then discuss about the serial and the parallel grounding, their pros and cons. And of course, we will continue with the guarding and the driven shields. Near the end, we will discuss a little bit about the analog signal sampling, about the sampling theorem, about aliasing phenomenon using the anti-aliasing filter, etc. And at the end, we will finish with the interfacing of digital input-output applications and their usage. Now let's start with some basic introduction to sensors, their properties, their characteristics, some basic models, and some basic concepts about what is data acquisition and what are actually the properties of data acquisition systems. So what is a data acquisition systems? What we could say is that a data acquisition system is a device or an integrated system which is used to collect information about the state or the condition of various parameters of any process. For example, if we collect a day-to-day temperature of a particular location, we can call that is a data acquisition. If a person is recording the level of a water storing tank, for example, into a piece of paper, what he is actually doing is performing the task of a data acquisition system. However, with the advancement of digital electronics, various electronic devices have been developed which actually use this job instead of the person itself, and it is doing recording or logging jobs. Although there isn't a strict definition of a data acquisition, but we could say in a broader sense, we could say that a data acquisition is the process by which physical phenomena from the real world is transformed into electrical signals which are measured and then converted into a digital format for processing, analysis, and further storage by a computer. Although concepts like data acquisition and test and measurement can be surprisingly difficult to define completely, most engineers and scientists agree that there are two common elements. And these elements are a computer, which is actually used to program, test equipment, and manipulate of storage data, and data acquisition plug-in boards, external board chassis, or discrete instruments. The difficulty which is involved in differentiation between the terms data acquisition and test and measurements blur the boundaries that separate the different types of instrumentation in terms of operation, features, and performance. For example, some standalone instruments now contain card slots and microprocessors. Moreover, they use operating systems and operate more likely like computers than like traditional instrumentation. On the other hand, plug-in boards can transform computers into multi-range digital multimeters, oscilloscope, or any other type of instruments, and can control them by some user-friendly virtual instrumentation from panels. For the sake of simplicity, in this talk we will use the term data acquisition broadly, which refers to a variety of hardware and software solutions which are capable of making measurements and controlling external processes. So what is a typical data acquisition system? Nowadays, most data acquisition systems are integrated with computers, sensors, signal conditioning devices, etc. And the function of this kind of data acquisition systems varies from simple recording of process parameters to control of industrial systems. This kind of systems basically have a hardware and a software part. The hardware parts are given with the 3 bullets on these slides. And these are the sensor or transducer, then a signal conditioning, and a data acquisition hardware. In general, we could say that the sensor or transducer converts the input energy related to the physical phenomena which is being measured from one form to another form, for example, such as resistance or capacitance or electrical voltage, etc. However, sensor signals are often not directly compatible with the data acquisition hardware. Now, to overcome this incompatibility, the signal must be properly processed with the signal conditioning circuits. For example, amplifiers, filters, sensor bridges, and so on. On the other hand, the main function of the data acquisition hardware is to convert the pre-processed analog to digital signals, or vice versa, and properly respond to the commands from the computer to the measurement systems. Finally, the data acquisition software allows exchanging information between the computer and the hardware. For example, typical software action would be to configure the sampling rate of the data acquisition board and to acquire some predefined amount of data. Now let's discuss a little bit about what is a sensor. To answer the question, what is a sensor, we have to understand its purpose. So, the purpose of a sensor is to respond to some kind of an input physical property, or a stimulus, and to convert it into an electrical signal which is compatible with electronic circuits. There are different types of sensors for more or less any physical quantity from the real world, as we can see in the figure. For example, let's say a temperature or a humidity or a, let's say, fluid flow, acceleration, or any kind of other physical quantity. We could say that a sensor is a kind of translator or generally non-electrical quantities into an electrical values. When we say electrical, we mean a signal which can be channeled, amplified, and modified by electronic devices. The sensor's output signal may be in the form of voltage, current, or a charge. This may be further described in terms of amplitude, polarity, frequency, phase, or digital code. This set of characteristics is called the output signal format. Therefore, a sensor has input properties of any kind and electrical output properties. In general, any sensor is an energy converter. So no matter what you try to measure, you always deal with energy transfer from the object of measurement to the sensor. The process of sensing is a particular case of information transfer, and any transmission of information requires transmission of energy. Of course, one should not be confused by an obvious fact that the transmission of energy can flow both ways. It may be with a positive sign as well as with a negative sign. That is, energy can flow either from the object to the sensor or from the sensor to the object. Now, the term sensor should be distinguished from the term transducer. Transducer is a converter of any type of energy into another, whereas the sensor converts any type of energy only into electrical signal. For an example, transducer could be a loudspeaker, which converts an electrical signal into variable magnetic field and subsequently into acoustic waves, which in turn has nothing to do with sensing. On the other hand, the quantity conversion can be direct by using sensors, or it may require transducers as the sensor model shown on the block. So here, for example, we have a model of a chemical sensor which converts energy from a chemical reaction into heat. This is transducer. And another part, which is actually a thermopile, a transducer 2, which converts heat into electrical signals. All this combination of two transducers actually make one union, which we could say that it is a sensor. As a response of the physical quantity which is being measured, the sensor produces an output signal in a form of voltage, current, or a charge. Now, our goal is to measure particular parameters of the electrical signals in order to deductively determine the physical quantity. Hence, the voltage, current, or a charge may be used to describe the signal's amplitude, frequency, phase, duty cycle, or digital code. All these parameters are subject to measurements with the data acquisition hardware, as we referred to in the previous slides. There are two signal types, analog and digital signals. The analog signals are continuous, meaning that they can have infinite range of amplitude values. On the other hand, the digital signals are discrete and they have finite range of values. For example, a binary digital signal has two values, a logical 1 and a logical 0. The advantage of digital signals is that they can be directly interfaced with the data acquisition hardware, concerning that it is a digital system. On the other hand, the analog signals must be initially converted into digital domain by using an analog to digital converters. The good point is that most commercial data acquisition systems contain standardized analog input channels with built-in analog to digital converters. On this slide, we can see an analog signal and its parameters. We can say that the basic parameters of an analog signal is the voltage level, and actually we can define the voltage level in different ways. We can say that the maximum amplitude is one parameter of the voltage level, or the peak-to-peak value of the amplitude, or for example, root mean square value of the amplitude. Next, we analyze the shape of the analog signal. So what we can see here is the sine wave shape, but it can be of any other shape, for example, triangular or square, or for example, arbitrary waveform. Then we analyze the phase of a signal. Here we see two signals, one with red color, and it has actually a phase shift of 0, and a blue signal, which is positively phase shifted comparing to the red signal. Then we analyze a period, which is actually one full cycle of the signal, and then we can define the frequency, which is actually the number of cycles of the signal for a given time. When we discuss about digital signals, we have more or less some similar parameters as with the analog signals, but also we have some original ones. For example, the state of the digital signal, what is that? So we have, in this example, we have a binary digital signal, and in the binary digital signals we have two states, a logical 1 and a logical 0 state. As with the analog signals, of course, we have a period and we have a frequency, but also we can analyze the duty cycle of the signal. And what is a duty cycle? The duty cycle is actually a ratio between the duration of the positive pulse of the digital signal and the negative pulse of the signal. So far we have discussed about the sensors, their properties, and some basic understanding of the data acquisition systems. Now we will continue with the signal sources and the wiring with the data acquisition systems. Okay, so far we have introduced sensors and some basic information about the data acquisition systems. Regarding the connection with the data acquisition systems, we have two types of signal sources: a grounded signal source and a floating signal source. A grounded source is one in which the voltage signals are referenced to the system ground. Now, having in mind that such sources use the system ground, they share a common ground with the measurement device. On the other hand, in a floating signal source, the voltage signal is not referenced to any common ground. The system ground can be sometimes wired to the source casing, if there is any, but the ground is never connected to the source leads. Some common examples of floating signal sources are, for example, batteries, thermocouples, transformers, insulation amplifiers, and so on. On this slide, we can see the measurement of grounded signal source with a ground referenced measurement approach. It is known that a grounded signal source is best measured with a differential measurement system. On this illustration, we can see the disadvantages of using a ground referenced measurement system to measure a grounded signal source. In this case, the measured voltage, Vm, here, is the sum of the signal voltage, which is here noted as Vs, and the potential difference, delta Vg, between the signal source ground and the measurement system ground. So this is Vg. This potential difference is generally not at DC level, but rather a noise at the power line frequency. Also, the loop between the signal and the system's ground introduce DC and AC noise and worsen the measurements. This is because the potential difference between the two grounds causes a ground loop, and the ground loop actually introduces a current to flow between the grounds of the circuit. On the other hand, we can still use a ground reference system if the signal voltage levels are high and the interconnection wiring between the source and the measurement device has low impedance. In this case, the signal voltage measurement is degraded by the ground loop, but the degradation may be tolerable. Another very important thing is that we must observe the polarity of a grounded signal source before we connect it to the ground reference measurement system, because the signal source might be shorted to ground, which actually can damage the signal source. When we measure grounded signal source with differential measurement setup, we solve the problem stated in the previous slide. Namely, as we can see in this case, the measured voltage cancels the contribution of the potential difference between the signal source ground and the measurement system ground, which is actually delta Vg. And therefore, in this case, no ground loops are introduced. In this slide, we analyze the measurement of floating signal source. In this case, we can measure the floating signal source with both differential or ground referenced measurement configurations. However, in the case of differential measurement setup, we have to make sure that the common mode voltage level of the signal with respect to the measurement system ground remains in the common mode input voltage range of the measurement device. To set this voltage level to some reference, we can use resistors as shown in the figure. So here we use resistors R1 or R2. In case if we do not use resistors, the source will be truly floating, and it is not likely to remain within the common mode signal range of the amplifier. As a consequence of this, we will have saturation of the amplifier. On the other hand, there is no problems of using grounded reference configuration to measure floating signal sources. Moreover, no ground loops will be created in such case. In this slide, we would like to define what is a normal mode and a common mode voltage. These two terms actually appear frequently in discussions of analog inputs, and they're normal mode voltage and a common mode voltage. It is very important to understand these terms when it comes to selecting and making the best possible use of the data acquisition equipment, particularly if we want to minimize the effects of noise. One definition of the normal mode voltage, which actually is noted as VNM in the figure, is a noise voltage that appears across the inputs of the amplifier and thereby adding to the input. Normal mode specifications are usually given at frequencies or frequency ranges where sources of the noise are most common. For example, 50 Hz or 60 Hz, which actually is the frequency of the power line cables in Europe or the USA. The measure of an amplifier's ability to reject noise while passing the DC and low frequency signals is a parameter which is called normal mode rejection ratio. In opposite to the normal mode voltage, common mode voltage, which here on the figure is noted as VSM, appears between the amplifier's input and the ground, Both inputs see the same common mode voltage in addition to the voltage differences attributable to the signal. As we mentioned previously, the operational amplifiers amplifies the difference in voltage appearing at its non-inverting input and inverting inputs, and it will reject the signal appearing at both inputs. The degree of this rejection is what is called a common mode rejection ratio. So, improper grounding is a common source of problems which actually affects analog measurements. A perfect circuit ground would have potential of 0 volts with reference to earth ground and would have an impedance of 0 ohms at any frequency. But in reality, a good grounding requires some effort to achieve this, but actually it can never be perfect, especially not at all frequencies. When the data acquisition equipment is supplied from the power line grid, in theory the chassis will be at ground potential. However, there can be a considerable electrical path and significant resistance between the chassis and the true ground. On the other hand, there should be no problems as long as the chassis is used as a central grounding point for all other sensors and all other equipment. When instruments, sensors, and other components of the data acquisition systems are plugged into the power outlet at different physical locations in a given facility, their chassis can be at slightly different ground potential. The resulting voltage between these different grounds can cause actually the current to flow through the cable shields or other parts of the ground system. This will result in a formation of the ground loop, which actually is given here on the figure. So this is a ground loop. Actually, the ground loops can occur in any type of measurement systems, but they're most problematic for analog measurements. For ground reference measurements, ground loop results in currents which flows through the cable shields. On the other hand, in the case of differential measurements, the ground loop voltage can contribute to the common mode voltage. As a result, we can have measurements which are degraded by noise or suffer from the reduced signal input range. So the terms bipolar and unipolar are normally used to describe whether a signal remains positive with respect to ground or whether it can also assume a negative level. These terms can apply to inputs as well as outputs. A bipolar signal can be positive or negative with respect to ground, while a unipolar signal generally goes no lower than 0 volts. The main benefit of using a unipolar range for digitized analog inputs or outputs is to improve the resolution. In fact, the available number of analog to digital or digital to analog resolution bits actually remains the same, but it is divided between only half of the total voltage range of a bipolar configuration. If we compare the single-ended, or as we call the ground reference configuration, with the differential input, we can observe that the differential setup will usually offer better noise immunity. And this is especially very important in systems that use data from a number of different sensors, especially if they're located at a long distance. So now I would like to show you some practical experiment which actually can show a test for a single-ended versus differential configuration respecting to the noise immunity. So here we can see an experimental setup where we have a noise generator, and we will use this port, which actually is minus 20 decibels of noise, a white Gaussian noise. Then we have another, or an amplifier, and with 2 channels, because we need to implement both differential or single-ended configuration, and on both of the channels we can actually adjust the gain. And here we will use as an input, we will use a sine wave with a frequency of 2 kHz. Now I will connect an oscilloscope on the sine signal so we can see its shape. So here we can see that the frequency of the signal is around 2 kHz. And now we will connect actually the sine signal at one input of the amplifier, and we will use also the noise generator, the white Gaussian noise, to connect it to the other input of the amplifier. And now we'll see the wave shape of the signal on the oscilloscope. As we can see now here, we have a noisy signal. And also on this experimental board, we can actually increase or decrease the amount of noise. And also we can decrease or increase the signal itself. So this is actually the single-ended configuration. We can see that the noise is affecting a lot of the measurements. And now, if we connect this lead to this point, we will use the differential setup, and now in that case we will see the difference. So this is the differential setup. We can see that the amount of noise in this case is lot smaller, lot less lower, which confirms actually our previous comments and conclusions. And this is again the single-ended configuration. Every data acquisition system is affected by noise, and actually the noise can reduce the effective resolution of the data acquisition system itself. So therefore, in the following slide, we will discuss about the noise interference and the noise interference reduction techniques. Any sensor, no matter how well it's designed, never produces an electric signal which is an ideal representation of the input physical quantity which is being measured. One of the causes for that is actually the noise interference effects. The noise in the sensors and the circuits may be a substantial source of errors, and therefore we have to consider it very seriously. On this slide, we show two types actually of noise: inherent noise and interference, or as we call it, transmitted noise. Inherent noise is actually the noise which is coming from the electronic components which are used to build the data acquisition systems. For example, passive components, resistors can generate significant amount of thermal noise, or active components, for example, transistors or operational amplifiers, they can add offset, or they can actually generate noise by themselves. And the second group is the interference or transmitted noise, which is actually the noise coming from the outside of the circuit. On the figure, we can see a block diagram of the transmitted noise propagation. At the beginning, we have a noise source, and the source can be different. For example, power supply, especially if switch mode power supplies are used, they can generate transients, or for example, thermal variation, radio frequency electromagnetic fields, or the ambient humidity or the temperature can also be cause for generation of noise, ionizing radiation, or other different sources of noise. This noise is coupled to the receiver, which is actually the sensor, by inductive or capacitive coupling, which is actually coupling through the wires or through the packaging or the casing of the data acquisition system. The transmitted noise can be additive or can be multiplicative. On the figure, on the left-hand side, the figure 8, we can see, for example, of a wave shape of a pure signal. And on the right-hand side, on the figure B, we can see actually the signal which is affected by additive transmitted noise. The transfer function of the additive transmission noise is given here. So we can see Vs is the signal and En is the noise. The noise is added to the signal. So we can see now how the noise is affecting the wave shape of the measurement. However, the noise can also be multiplicative. This is the transfer function of the multiplicative transmitted noise. And the noise function is here denoted as N. And as we can see here, now the noise is actually modulating the signal which is being measured. And therefore, the noise effects are much more radical. And this we can see from the figure. Comparing to the previous one, this figure is much more noisy. As we mentioned in the previous slide, the noise can be transferred to the data acquisition system by actually a capacitive or inductive coupling. On the left-hand side, we can see some figure of a capacitive coupling. Here we analyze two wires, pattern 1 and pattern 2, and we have a noise source which is connected to the conductor number 1, pattern 1, and the ground of the system. And on pattern 2, actually we have some kind of load which is connected between the conductor and the ground. Having in mind that the conductors are metals and they have in between they have some kind of dielectric, actually they form a parasitic capacitance. So the equivalent circuit of the capacitive coupling is given here on this figure. And now we can see that actually the noise source is divided through the impedance of the capacitor C and the resistance of the load R. And in that way, we have an induced noise, which is Vn, denoted as Vn, on the conductor number 2. On the right-hand side, we can see the inductive coupling. The inductive coupling appears because in the conductor number 1, which is denoted as pattern 1, actually we have a current ES which is flowing through the conductor. When a current is flowing, a magnetic field is formed around this conductor, and because we have a mutual inductance between these two conductors, pattern 1 and pattern 2, we have a voltage Vn, noise voltage, which is induced in the conductor number 2. And this is the equivalent model of the circuit when we have inductive coupling. On the bottom of this slide, on the left-hand side and on the right-hand side, we can see the transfer functions of the noise which is actually affecting the data acquisition systems. The data acquisition systems can be also affected by so-called Seebeck noise. On the figure on the right-hand side, which is this is figure B, we can see the Seebeck effect on the junctions on the connection between the sensor and the signal conditioning circuit, which is actually some kind of amplifier. On the junctions, we have two different metals which are joined here, and because when two different metals are joined in one point, in that point we have generation of a voltage. And on the left-hand side, we can see, for example, a function of a temperature function, and the introduced voltage when we have different types of metals. For example, this curve here is if we have 64% of tin and 36% of lead. And we can see that for example, on the room temperature around 25 degrees, we can have a Seebeck voltage of maybe around 40 microvolts. Sometimes this Seebeck effect can be significant, and sometimes maybe not significant. It depends on the precision of the circuit and the data acquisition system. So now we know that the noise is unavoidable in the data acquisition systems. So in the following slide, we will discuss a little bit about the possibilities for elimination of that noise. And we will do that by elaboration of the grounding and the shielding techniques. Grounding is one of the primary ways of minimizing the unwanted noise. When we combine proper use of grounding and cable shielding, we can solve most of the noise problems in the data acquisition systems. So what is a ground? In electrical engineering, ground or earth is the reference equipotential point at any electrical circuit from which voltage are measured. It is a common return path for electrical current and a direct physical connection to the earth. Usually the grounds fall in one of the two categories: safety ground and the signal ground. The difference is that the safety ground is usually at earth potential, whereas the signal ground may be or may not be at earth potential. Now the signal grounds can be subdivided in three categories: single point grounded systems, multi-point grounded systems, and hybrid grounded systems. However, in all three categories, we have to consider the two key points, and those are: all conductors have finite impedance consisting mainly of resistance and inductance, and two physically separated ground points are usually not at the same potential. When we are talking about single point grounding, we have two possibilities for their implementation. On the left-hand side, we can see the series single point grounding, and on the right-hand side, we can see parallel connection of the single point grounding. However, in both situations, regarding to noise, the single point grounding is the most undesirable grounding system. What we could say in both series or parallel connection is that the conductor lengths from the circuits, circuit 1, 2, or 3, to the equipotential point are different. And that means that the impedance will be different. So in situations when we have currents which are flowing from the circuits to the system grounds, all circuits 1, 2, or 3, in both situations, parallel or serial, will be at different potential. And that means that we will have a different potential difference between the circuits, and that means that we will have appearance of a ground loops. Moreover, if the current which is flowing from the circuits to the system ground is with higher frequency, then the impedance of the wires will be even higher, and the potential difference between the circuits will be also even higher. On the other hand, on a higher frequency, actually the grounding system in both series or parallel connection can act as antenna and can irradiate noise in its surrounding. Multi-point ground system is used at higher frequencies in order to minimize the ground impedance. In the ground system shown on the figure, the circuits are connected to the nearest available low impedance ground plane, which is actually usually the system's casing. In the multi-point grounding, we have to keep the ground connections as short as possible in order to minimize their impedance. On the other hand, the multi-point grounding should be avoided at low frequencies because all currents from the circuits flow through a common ground impedance, and that is the ground plane which is shown here on the figure. This is the ground plane. On this slide, we can see a hybrid ground. On the left-hand side, we can see a circuit which actually acts like a single point ground at a low frequencies and as a multi-point ground at a high frequencies. Let's consider, for example, that we have a DC component. At a DC component, the impedance of these capacitors is very high, is actually theoretical infinity. So that means that we have an open circuit here, and we have single point serial connection. And if we have a high frequency, then the impedance of the capacitor is nearly zero, so we have a multi-point connection. On the circuit on the right-hand side, it is more or less similar, but actually this circuit acts like a single point ground at high frequencies and a multi-point ground at low frequencies. The interference due to the electric fields can be significantly reduced by shielding. What we shield is usually the sensor and the circuits, for example, the signal conditioning circuits. This is especially important if we have high impedances or we use nonlinear components. So what is the purpose of the shielding? We can say that the shielding has two purposes. First, it concentrates the noise to a small region, which will prevent the noise from getting into nearby circuits. And second, if noise is present in the circuit, the shields can be placed around the critical parts and prevent the noise from getting into sensitive portions of the detectors and the circuit. We have two types of shields. an electric shielding and magnetic shielding. On the figure A, on the left-hand side, is what we can see is a capacitive coupling of the noise, what we have discussed in the previous slides. So here we see the noise source. This is the capacitive coupling, actually the parasitic capacitance, and this is the load. And as we discussed, here we have some impedance divider, and by that impedance divider we have a noise Vn which is induced into the data acquisition system. When a shield is added, the change to the situation is shown in figure on the right-hand side. This is the figure B. If we assume that the shield has a zero impedance, then the noise at the left side will be actually the noise voltage En divided by the impedance of the capacitor C1. However, on the other side of the shield, the noise current will be near to zero because there is no driving source on the right side of the circuit. Therefore, the noise voltage over the receiving impedance will also be zero, and the sensitive circuit becomes effectively shielded from the noise source. Here on the left-hand side we can see different possibilities of electrical shielding. And on the right-hand side we can see practical rules that must be observed when applying electrostatic shields. And these rules are: the electrostatic shield, to be effective, should be connected to the reference point of any circuit contained within the shield. This means that if the signal is connected to the ground, the shield must also be connected to that ground. And this is shown on the figure A. The second rule would be, if a shielding cable is used, its shield must be connected to the signal reference node at the signal source side. This is shown on the figure A. So we connect it to the ground on the signal source side. If the shield is split into sections, which can occur, for example, if we use connector in connecting the data acquisition systems, the shield for each segment must be also tied to the other segments and to the signal reference node. And this is shown on the figure B. So these are different segments, and we connect all the segments to the grounding. Also, a shield must be grounded only at one point, and if possible, we ground it next to the sensor. Moreover, a shielded cable must be never grounded at both ends, because then we will have a ground loops. If a sensor is enclosed into a shielded box and data is transmitted through the shielded cable, the cable shield must be connected to that box. This is also shown here on the figure C. And also the last rule would be that it is advised to use short connection wires to minimize the inductance. And this is very important, especially when both analog and digital signals are transmitted into data acquisition systems. So proper shielding can dramatically reduce noise resulting from electrostatic and electrical fields. However, unfortunately, it is much more difficult to shield against magnetic fields because it penetrates conducting materials. A typical shield placed around a conductor and grounded at one end has little effect on the magnetically induced voltage in the conductor. For improving the low-frequency magnetic shielding, a shield which constitutes of a high permeability magnetic material should be used. However, the effectiveness of the shield drops at higher frequencies and for stronger magnetic fields. At higher frequencies, an effective magnetic shielding can be accomplished by using a very thick material, thick actually metal shields. Since magnetic shielding is very difficult, the most effective approach at low frequencies is to minimize the strength of the magnetic fields, also to minimize the magnetic loop area at the receiving end, and to select the optimal geometry of the conductors. Also, we have some practical rules when it comes to magnetic shielding, and those are: we have to locate the receiving circuit as far as possible from the source of the magnetic field. Also, we have to avoid the placing wires which are parallel to the magnetic fields. Also, it is advisable to use a twisted pair of wires for conductors which are carrying high-level currents. And also, we have to shield the magnetic field with an appropriate material for the frequency and the strength. And now let's go to the last part of our presentation, and that is interfacing analog and digital signals to the data acquisition systems. The analog signals are interfaced to data acquisition systems by using an analog to digital converters. Basically, the analog to digital conversion is a three-step process which covers sampling, quantization, and coding. On figure A on the left-hand side, we can observe a pure sine wave analog signal. The first process, which is sampling, as its name suggests, is selection of amplitude values from the analog signal. In general, we can have uniform or non-uniform sampling. But on the example, which is shown on the figure on the right-hand side, we have used a uniform sampling. What is important here is that the sampling frequency must fulfill the Shannon sampling theorem, or also sometimes is referred to as Nyquist criteria. The Nyquist criteria is that the sampling frequency must be at least 2 times higher than the frequency of the analog signal. The second phase is discretization of the amplitude of the signal according to existing quantized level of the AD converter. The number of quantization levels of the analog to digital converters is determined by its resolution. For example, if we have a 10-bit AD converter, we will have 1024 quantization levels. It is clear that the more quantization level of the AD converter has, the more accurately the signal will be represented. Finally, the last phase of the AD conversion is the coding. In this phase, the samples are transformed into digital codes, which can be processed with the digital systems. On this slide, we analyze the frequency spectrum of the analog signal prior and after sampling. On figure A, on the left-hand side in the upper corner, we see a pure signal spectrum which contains only single frequency component, which is FA. When this signal is discretized, the signal spectrum changes as shown on the figure B on the right-hand side on the right corner. What we can see is that in such case, a multiplicative components in the frequency spectrum appears. And those are given here. So this is the first multiplicative component, the second one, the third, and so on. The multiples of the frequency spectrum are related to the integer number of the sampling frequency. The same effect appears if a signal with a wider signal spectrum is discretized. The signal band is denoted as V on the figure below. So this is the signal bandwidth. If it is discretized, then we will obtain the following signal spectrum. However, in this case, we will obtain copies of the signal band and multiples of the sampling frequency. The problem with the discretization appears when the signal band is too wide, so wide that it overlaps with different multiples of the frequency spectrum. That is an undesirable effect, which is called aliasing. In fact, aliasing irreversibly distorts the signal, and it can never be originally reconstructed afterwards. To prevent the aliasing phenomena, we can use anti-aliasing filters. These filters are placed in front of the AD converter and in fact restrict the bandwidth of the signal, so no aliasing can occur, assuming that appropriate sampling frequency is defined. The cutoff frequency of the filter is usually placed at the highest frequency of the analog signal. So here is the analog anti-aliasing filter. We place it just before the analog to digital converter, and here the output of the ADC goes to the data acquisition card. On the other hand, the parameters and the type of the anti-aliasing filter must be appropriately defined according to the predefined criteria. Among other, there are three basic filter types: Bessel, Butterworth, and Chebyshev. Bessel filter has the smoothest phase to frequency and amplitude to frequency characteristic, but has low attenuation in the stop band. On the other hand, Chebyshev filter has high attenuation in the stop band, but introduces ripples in the amplitude characteristic in the passband. Butterworth filter has intermediate smoothness in the passband and attenuation in the stop band. Now we will show a demonstration of discretization of an analog signal. So here it goes. Here we have a voltage-controlled oscillator. So we can change the frequency by changing the voltage of the oscillator. Then we use a sample and hold circuit for discretization. It has actually three inputs, but we will use two. The first input is for the analog signal, and the second one is for the clock, for the digital signal. We will discretize analog signal with 2 kHz of frequency. Here it is. We show it on the oscilloscope. And also, now we will see the digital signal, which we will use for discretization. We can change its frequency. We will actually adjust it to around 18 kHz, and that means around 9 times higher than the frequency of the analog signal. Here, this is 18 kHz. Just to see it a little bit better. Okay. So now we connect the analog signal to the input of the sample and hold circuit. And we connect the digital signal to the clock of the sample and hold circuit. And we will observe the output signal with the oscilloscope. This is the discretized signal. We'll just make a pulse here, so we can count. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. So it has 9 samples per one period, which is actually exactly the ratio between the frequency of the digital and the analog signal. Now we can reconstruct the signal by using a low-pass filter. This is a tunable low-pass filter. We can change the cutoff frequency and the gain of the filter. So now we connect the discretized signal to the input of the filter, and we will observe the output signal from the low-pass filter on the oscilloscope. Here it is. So now it's back into a sine wave. We can play a little bit with the cutoff frequency. It has to be just a little bit above the frequency of the signal, of the reconstructed signal. But now we can change actually the clock frequency. Let's go down and see which is the minimum frequency in practice that we can use for discretization of the signal. It's around here somewhere. Now let's see the discretized signal again. As you can see, actually we have 4 samples per period, and we expected 2 according to Shannon's theory, but actually in practice it's very hard to realize it as in theory. In fact, in practice the sampling frequency has to be a little bit higher than what is suggested with the Shannon sampling theory. In practice, maybe more than 10 times the frequency of the signal itself. Okay. On this slide, we analyze connection of a discrete mechanical switches with the data acquisition systems. To do so, Usually a pull-up or pull-down resistors are used. On the figure on the left-hand side, we see a mechanical switch connected to a ground and a pull-up resistor which is connected to the power supply. When the switch is pressed, the digital channel is shorted to ground, and when released, it is connected to the power supply of the resistor. In such way, we perform digitalization of the switch signal, where its digital levels are controlled with the power supply voltage. On the other hand, what we see here is a reverse logic, because the circuit generates a logic 0 when the switch is pressed. To reverse the polarity of the digital signal, we must interchange the position between the resistor and the switch, and in such case the resistor will become a pull down. Another problem that can arise here is the mechanical oscillation of the switch in the process of switching. This can cause generation of several digital pulses in a short duration after the switch has been pressed, and can cause a false reading. And that is shown on this figure here. So this is bouncing period after the mechanical oscillations of the switch. And this can be solved in two ways: by using a buffers with input hysteresis function, for example, a Schmidt trigger buffer, or a flip-flop circuit, which is actually proposed here. We have discussed about the importance of proper grounding and the avoidance of the ground loops. Therefore, sometimes the digital systems must be galvanically separated from the data acquisition systems in the measurement or the control phase. On the left figure, we can see a digital isolation of digital signal intended to be processed with the data acquisition system. And on the right figure, we see a digital isolation for load controlling purposes. In both cases, an electric component which is called optocoupler is used. The digital signal biases the LED diode, which in turn saturates the transistor. And the diode and the transistor share the same casing. When the transistor saturates, it either serves as a pull-down switch in the first case, or as a pull-up switch in the second case, and controlling the load. Now we have come to the end of the presentation. I hope you enjoyed the lecture and you find it useful. Now, once again, I would like to highlight that this presentation was supported by the Erasmus project, Innovative Teaching Approaches in Development of Software Design Instrumentation and its Application in Real-Time Systems. Here you can find also the logos of the partners within the project. And also I would like to say that this video material will be used as an intellectual output in the framework of the mentioned project. Thank you very much.